Welcome back. So, in today's video lecture, we will look at the contact angle for non-ideal cases. Okay. In a couple of lectures ago, we have looked at the N-Dupre equation derived for ideal case, right? So, in today's equation, we will look at the contact angle for non-ideal case, and along with that we will also look at the application of N-Dupre equation. Okay, so these are going to be the today's the learning objectives of this lecture. Okay, let's begin. So as I just mentioned, so we will look at the contact angle for non-ideal cases. Okay, contact angle for non-ideal cases, right? And apart from that, we will also look at the application of N-Dupre equation in this lecture. All right. So we know that the contact angle of N-Dupre equation can be described in this way, right? So this we have already looked at in previous lecture, right? So this equation describes this phenomenon. Whenever you spread place a droplet of liquid on a surface, okay, a smooth surface, okay, the droplet may wet or retract depending on the nature of the solid, right? Solid surface, right? And this behavior is captured by this N-Dupre. So this is nothing but using N-Dupre equation, one can understand the nature of the surface by evaluating the three-phase contact angle. Three-phase contact angle is given in this schematic also. This is nothing but three-phase contact angle because at this juncture, all three phases exist, like solid gas, solid liquid, and solid liquid gas, right? That's why we call theta measured at this juncture as three-phase contact angle. So remember, when we derived this equation, we made some assumptions, which means that this equation is applicable. Only these assumptions are met, right? So the first and foremost assumption that we mentioned was equilibrium is attained, right? So this theta that we measure is equilibrium contact angle. Okay, so that is our first assumption. The second and third assumptions are it is applicable for surfaces with homogeneous and surfaces surfaces with which are chemically homogeneous and which are smooth, right? So which means that this equation is not applicable for surfaces which are homogeneous, okay, which are heterogeneous, and surfaces with roughness, right? So these two, how do we encounter whenever we face this kind of a situation? How we can revisit the equation? That is what exactly we are going to look at. And the last one is nothing but the no absorbing of liquid by the surface. This part we will cover in the following lecture, but in today's lecture we are only going to look at how we can tackle when we deal with the surface with heterogeneous and surface with the roughness. Okay, so we have got two models, right? One is nothing but Casey-Baxter, right? The other one is Wenzel-State. Okay, so this Casey-Baxter model comes from the Casey's law itself. Okay, so what does this law says is that whenever you have surface with which is porous in nature, right? So in such case, let's say I can draw a schematic, right? Okay. Let's say we have a surface where we have type 1 impurity, and we have, okay, let's say we have type 1 impurity. At the same time, we also consider surface with the porous, porosity, right? In that case, you have a segment where you have surface corresponds to type 1, okay, and the zone where you will have a zone which is filled with air pockets. So in this case, this particular zone is filled with air pockets because of the the factor that we mentioned right just now, which is the surface which is which has high porosity, right? So in this case, so what will happen is whenever we spread a droplet, this in this zone, because this zone is filled with air pockets, water, it doesn't allow water to penetrate inside this zone, right? So in such case, we can assume that theta will be 180 degree, which means that it will completely the water molecule cannot enter into this zone, so that the theta in this case will be the droplet in this case will not spread at all. So in such case, we can say theta, we can denote theta as 180 degree. Okay, so whenever we deal with a combination of properties, right? So we always have used what is known as lever rule whenever we deal with mixture, or whenever we deal with a combination of properties, right? So in this case, we know the Young-Dupre equation. I denote Young-Dupre equation with the theta with y as in the subscript, okay, along with the theta, so that this is nothing but theta for the Young-Dupre case, right? So which is nothing but gamma Sg minus gamma Sl by gamma Lg. So we know that the same theta will not be applicable here, but whenever we want to measure theta, in this case a property, whenever we deal with a mixture or a combination of several properties, in such case we use lever rule, which is something like mole fraction into the particular property, right? So we use something like this, mole fraction into the property, okay, correspond to particular compound. So in this case, what we can do is, since we deal with the surface, we can call it as fraction 1. So 1 represents type 1, right? So the fraction of type 1, right, molecule, which is F1 multiplied by cos theta 1, right, because this theta corresponds to type 1 surface. Then you can say F2 cos theta 2, okay, because for brevity we are only considering two kinds of surfaces, right? One is air pocket itself, another one is a type 1 surface. So in this way you can also so you can also simplify this equation in this way, that is nothing but F1 cos theta 1 plus 1 minus F1, right? Since just now we mentioned that the air pocket will not allow the water molecule to penetrate inside, so we can theoretically assume theta to be 180 degree, which means that, so cos 180 will be minus 1, so we can simply write this equation as minus 1 minus F1 itself. So this is how the equation can be modified. So in this way, I want to denote theta with a subscript C, which represents Cassie's model, right? So this equation, we can obtain a compact equation from the Young-Dupré equation that we just now, shown. Which I just now shown. So now this is nothing but Casey's law itself, right? Right. Now, what is Casey-Baxter? So that is what we have to look at. What is Casey-Baxter? Okay. So this is a modified version of Casey's law itself. So in Casey-Baxter, what we consider is, instead of considering the air pockets, we consider different types of surfaces, right? We consider different types of surfaces instead of air pockets, right? So let's say you have a surface which has got different chemical heterogeneity, right? Okay. Right. So so you have, let's say in this case, we have type 1 impurity and type 2 impurity. So we considered two types of impurities in this case, just to understand, to get, for brevity, we have just considered two types of surfaces, but one can have numerous types of surfaces as well. We will see how we can obtain equation for cases where we deal with numerous types of surfaces. For now, we will consider only a surface which has two different types of chemical heterogeneities. Okay, one is type 1 and another one is type 2. So in this case, the same lever rule can be applied. So in this case, I will use cos theta as CB, which represents Casey-Baxter. Okay, so this can be written in this way, which is nothing but F1 cos theta 1 plus F2 cos theta 2. Okay, right? And so sometime you might deal with a surface, okay, with numerous chemical heterogeneities. In such case, you can simply represent the Casey-Baxter model in this way, which is simply nothing but summation I, okay, Fi cos theta I, right? Because when you have numerous types of surfaces, you can simply represent Casey-Baxter model in this fashion, right? Right. So the next comes the surface with the roughness, okay? So we have seen Casey's law. Whenever the surface, so you consider in this case surface with the porosity. The second one, what we dealt was Casey-Baxter. In this case, you have to consider surface with numerous types of chemical heterogeneities, right? The next one that we will deal with is surface with the roughness, right? So in this case, what we will have is the Wenzel model, right? Wenzel state, okay? Okay. So what does it represent? I mean, what does it says is that let's say you have a surface with roughness, right? Something like this, right? So this roughness indicates that the interfacial area, which is more than the surface area of the smooth surface itself, right? So because it has got more exposure, so the roughness factor will amplify the nature of the surface. Say for example, if the surface is hydrophilic, the roughness will make the surface more hydrophilic. It is because this interfacial area is more significant than the surface with the smooth surface, right? So on the other hand, if the surface is originally hydrophobic, the roughness makes the surface more hydrophobic, okay, than the previous case. So that's what we need to understand in this case whenever we deal with surface with the roughness. Okay, so Wenzel says that, so you can use the Young equation as it is, right? But with some correction factor, which is nothing but beta. So beta is nothing but the ratio of actual area to the projected area. Yeah. So ratio of actual area to the projected area. So so beta is always greater than 1 because actual area in the case of roughness, surface with the roughness is higher than the projected area. So so this factor will enhance the nature of the surface. If surface is hydrophobic, the roughness will make the surface more hydrophobic. If surface is hydrophilic, there also the roughness will make the surface more hydrophilic, right? So in this, these modifications help us revisit the Young-Dupré equation and use the modified equation, okay, derived from the Young-Dupré, depending on the situations we deal with, right? Right. So these are some deviations that we have seen so far. And one other, the other deviation that we have not looked at in this lecture is that what if the surface is imbibing in nature? If the surface is absorbing some amount of liquid, for such case, we will have to use a different equation, what is known as Washburn equation, which we will see in the not in today's lecture, but in following lecture we will see. So now we move on to the second aspects of our learning objective. That is nothing but the application of Young-Dupré. Application of Young-Dupré. So consider whenever we, especially in pharmaceutical industries or healthcare industries, whenever we deal with dry solid or dry powder and whenever we mix these dry powder or dry solids with the liquid, okay, it always generates some amount of heat, right, as a result of the mixing, right, soaking the dry powder into liquid. It releases some amount of heat, right? So although the fraction of heat that is released out of this process is not very significant, whenever we deal with product like API drug products or drug products, even a small amount of heat released from the from this process will make the product will deteriorate the product, right? So will affect the product quality. So that's why sometimes it is very important to understand. Okay, so whenever we deal with mixing and those operations, are we adding right amount of dry powder? Or are we mixing are we soaking these dry powders with the right amount of liquid? So these questions we often ask so that we can we can quantify the amount of heat released and if and then say that these factor will not affect the quality of the product. So that is the exact objective of this exercise. So first let us understand how this application of Young-Dupré can be utilized. So let's say we are talking about a scenario where you have dry solid, okay, and soaking that with the liquid and it becomes a wet solid, okay. So in this process, it releases some amount of heat, okay. So what will happen is let's say if you are calculating the delta H immersion, okay, which is nothing but H, wet enthalpy of wet solid minus enthalpy of dry solid. You expect that in this case some amount of heat is released, right? So this is what is our problem statement, okay. So how do we calculate this delta H immersion? So that is the question that we are trying to address, right? So before that, let's understand, what is the fundamental equation that we know in terms of Gibbs free energy, which is nothing but enthalpy minus Ts, right? S is nothing but entropy here, and T is temperature. And we also know Gibbs free energy in differential form, which is nothing but minus S dt plus V dP, okay, right? So at constant pressure, we know that dou G by dou T at constant pressure is nothing but minus S, okay, right? So sometime we also, refer to the Gibbs, right, excess free energy as G by A itself, which is Gibbs free energy measured per unit area. This is also nothing but gamma, which is surface tension. This notation is sometimes used without differential form. So G by A, Gibbs free energy measured per unit area, is nothing but surface tension, right? So what we can do is we can revisit the equation that we mentioned here, that is G, which is nothing but H minus Ts, okay. I can also slightly modify this equation so that I can bring this gamma into this equation, right? So what I will do is I will simply mention Gs superscript S, which represents excess Gibbs free energy measured per unit area, right? So you can also represent in the same way, you can also represent enthalpy superscript S minus T entropy superscript S, okay. So what it represents is we have normalized each term with respect to area, okay. So in this case, I can simply write G superscript S as gamma itself, okay. In this way, I could bring gamma into this equation. Then you have Hs minus, so this minus S is nothing but dou G by dou T, but minus S superscript S will be, in that case will be, plus T dou G S by dou T at constant pressure, right? So that is what we have to write here. Okay, so we know you can also write this as gamma, right? G superscript S is nothing but gamma. So you can write as dou gamma by dou Tp itself. So we know then what is H superscript S, which is nothing but gamma minus T dou gamma by dou Tp, right? So this we know, we have obtained from this equation. Now we know for H superscript S, but we are talking about delta H immersion, which is nothing but H wet means SL, right? Subscript SL. Then H dry solid, which is nothing but SD, right? So if I can, so then I specify delta H immersion superscript S, then I will use the notation same for all the term. In this way, I can rewrite this equation in this way, that is nothing but HSL is gamma SL, okay, minus T dou gamma by dou T gamma SL P, okay, minus HSG, I can write it as gamma SG minus T dou gamma SG by dou T at P, right? So we know that gamma SL minus gamma SG we have got here, okay? So this is nothing but gamma SL minus gamma SG minus, if I take out the T, then this is nothing but gamma SG by dou T P minus gamma SL by dou T P. Okay, so we know that if I apply minus everywhere, then I will be having, this will be gamma SG minus gamma SL, which is nothing but gamma LG cos theta itself plus T dou gamma LG cos theta divided by dou T at constant P, right? So if you expand this further, so you will have gamma LG cos theta plus T cos theta dou gamma LG by dou T P plus T gamma LG dou cos theta by dou T P. So if you see, all you need to know is what is the gamma LG and the regression of gamma LG and cos theta on T, right? In this way, you can calculate what is the delta H immersion of solid, dry solid, whenever it is soaked with liquid, right, immersed with the liquid, what is the amount of heat released from the process. So that is exactly what we calculate using this equation. So we this equation has been verified. Although we have we have several sophisticated techniques, okay, like calorimetric technique to measure this small amount of heat that is released. You can use this equation to complement the results, calorimetric results, right? To validate the results, right? So in this way, this equation can be used to compute the amount of heat released from the process, right? The quenching process, right? So we'll stop here. We'll continue from the next lecture. Thank you.